Welcome to Homework Lib.
Hi, so for solving this problem, the first thing that we need to have as information is the crystal structure for each sodium and for aluminum. So in the case for sodium, the structure that we're going to have is a BCC structure. We know that the constant, it is going to be equal to 4.3 angstroms, but this implies that we have two atoms per lattice. And each sodium atom only has one conduction electron. Now, for the case of aluminum, what we're going to have is that it is going to be an FCC structure. The lattice constant, it is going to be 4.0 angstroms. Whoop. So this implies that we're going to have 4 aluminum atoms per lattice. And aluminum is a trivalent compound, so this is going to have 3 electrons in the conduction band, each of the atoms. Okay? So this means that N, it is going to be the number. First of all, let's do the calculation for sodium. In the case for sodium, what is going to happen is that the value for N, it is going to be 2 atoms per lattice. We only have 1 electron per atom. This is the number of electrons in the conduction band. And if we divide it by the volume of the lattice, that it is going to be 4.3 angstrom cube, we are going to find the density of electrons in the conduction band. Of course, here, in order to simplify our result and to not do a lot of conversion factors, let's do it directly in meters. So this is going to be 4.3 times 10 to the minus 10 meters, and this value cube. So the result that we get from this is going to be 2.52 times 10 to the times 10 to the 28 meters to the minus 3. Okay, so with this result, and actually that is the only thing that is going to change in our calculations for both of this, in order to get the Fermi energy within the free electron model, we are going to do the calculations as follows. Remember that this mass is the mass of electrons, because those are the electrons that are responsible for the conduction band. 3 pi squared times n elevated to the 2/3. So the value in international units for h bar is 1.050546 times uh, times 10 to the minus 34. This is joule second. And the mass of the electron, it is going to be 9.109 times 10 to the minus 31 kilograms. Okay. Using these values, we get a Fermi energy for sodium equivalent to 5.02 times 10 to the minus 19 joules, which converting to electron volts is 3.13 electron volts. So next up, for aluminum, as we mentioned, since we are going to have 4 atoms per lattice, and each of one of them is going to have 3 electrons per atom, the value for n, it is going to be that number divided by the volume of the lattice. So in this case, the lattice is going to be 4 angstroms, so 4 times 10 to the minus 10 meters cube. The value for n thus becomes 1.88 times 10 to the 29 meters to the minus 3. And the Fermi energy, doing the same calculation, to the 2/3 is going to give us 1.91 times 10 to the minus 18 joules, or in electron volts, this corresponds to 11.95 electron volts. And that would be all for this problem. The main idea is that you need to know what type of lattice you have in each of the compounds to know how many atoms per lattice you're going to have, and using the valence electrons, how many electrons per lattice you're going to have. So once you have known that electrons per lattice, you can calculate the electron density, the conduction electron density that you're going to get. And that will be all.